So hello again. This is the bioelectricity course in week 8, the last week of our course. Here's where we are in the overall scheme of things. On the train, we've made plans, we've sold tickets, we've built our train, we had fun running the train, we watched the train, and now we want to control the train. And thereby we have our signal, the control signal to make the train stop and go as we wish to do it. In the bioelectricity framework, we also have done a whole series of things. We've made plans and especially talked about electricity in solution. We talked about energy. We talked about different components associated with action potentials and where they go. We observed their propagation. We watched a lot of details, and now we're trying to control them. Now, control, in the bioelectric sense, usually means stimulation, electrical stimulation. Electrical stimulation is a vast topic. People work on it for their entire lives. In trying to prepare this week's lectures, I have necessarily selected topics from among this larger group, and what I've tried to do was to stay focused, select topics that illustrated fundamental principles rather than getting off into a long list of the details of particular applications, even though those applications are very important in the particular context in which they exist. Now, with stimulation, as you can imagine, or at least a core consideration is the location of the stimulus electrodes as compared to the location of the membrane to be stimulated. Let's look at this 4 different ways during this week's work. First, we begin with Galvani's observation. These were really the original observations, at least as far as is recorded, of the effect of electricity on muscle due to stimulation. We'll look at how Galvani had things set up. Then we'll go through and look at spheres, at cylindrical fibers, and at field stimulation. It's interesting as you progress through these. Spherical cells, this is a topic of interest because of the theoretical value of looking at a situation with no geometrical complications. Spheres are as simple as they come. The cylindrical fiber, cuff electrodes with time, is an application that is used in some context, but not extremely widely used. On the other hand, it is a building block for the theory of field stimulation, and field stimulation is what is mostly done. So you might say we look at it historically, then we build up to field stimulation, which is where things really have application widely. So let's begin with a few very straightforward questions. These questions seem simple, but on the other hand, it is important to have in mind the answers, lest one lose the context in the search and examination of details. First, let's ask, what is meant by stimulation? So here's an old sketch from the 1700s of stimulation as done by Galvani. Galvani charged an electrode. So this is the electrode, maybe a pair of electrodes. He inserted a charge on these electrodes with some external source, a battery of some kind or some other process. Then he touched frog leg here, body of the frog there, and the consequence was a twitch. The frog leg jerked. So here's where it was, and here's where it went to. Stimulation producing contraction. historically the significance of this is not entirely what you would think. At the time it was done, there were no meters in the modern type, no voltmeters or oscilloscopes or computerized instruments, of course. So the twitch of the frog leg itself became a meter that showed whether or not an electrical charge was present in some device or instrument or other context. It was, if you will, the original voltmeter, although of course not called that. If we think about that experiment performed by Galvani in a more modern context, we'd say what happened was Galvani had a probe, and with his probe, he did field stimulation. That is, his probe established an electrical field here, and his probe was out in the field, away from the nerve. It nonetheless stimulated a nerve. The nerve propagated a series of action potentials here, here, here. As the action potentials reach the end of the nerve, they release neurotransmitters, indicated by these circles, which are chemical elements. The neurotransmitters produced additional action potentials and then resulted in contraction of the muscles of the frog's leg. Quite a complicated process, but all controlled, that is, initiated by the probe and by the electrical stimulus. People do essentially the equivalent of that right up until the present day. In bioelectricity, saying it in words, stimulation means, generally, the use of electrical currents to influence the action of excitable tissue. Quite often it's used to initiate action potentials. Perhaps the most common application that people think of are cardiac pacemakers. On other occasions, stimulation is used to stop action potentials. So stimulation is used in some cases for the relief of pain, and it's used in other cases to stimulate the brain in relation to Parkinson's disease and the relief of some of the symptoms. And in a general way, stimulation can be used to modify function in the sense of contraction or some other muscular function, not simply to control the electrical function, because the electrical function is the control system for quite a lot of mechanical function. So stimulation is a very important topic because it has so many applications. As we contemplate this beautiful topic, I brought you some beautiful pictures taken from the Sarah Duke Gardens of Duke University. Here's the first. Thank you for watching. We'll see you in the next segment.